All right, the last section of that review chapter, although chapter 2 is review also, is inverse functions. And we did this in class where I had no sleep and made terrible errors. But let's chat about inverse functions. So first thing we need to be able to do is verify that two functions are inverses of one another. And the whole goal of an inverse is that f is a function that takes x to y, right? Takes x as an input and gives out a y. And f inverse will take in a y and give out an x. So basically, we are swapping the domain and range, swapping our input and output for these two functions. And when we were in class, we did a really good job. You guys noted some things. First, in order to verify inverse functions, we had two ways to do this. One was we could make sure that if we looked at the graph in Desmos, that our actual result was a reflection over the x is equal to, or y is equal to x line. If that was true, then we could be pretty confident that we had done the right thing. So an example of that would be like, whoop, say we have that as our original graph. This is our y is equal to x line. What we would hope to see in our inverse function is something like that. So that was one way to check. The other was to use our composition of functions. If we throw the inverse function inside of the regular function, or vice versa, we should end up back with whatever value we plugged in. Because essentially what will happen in the first example, if we plug in an x, really it's more like plugging in a y, right? I mean, that's going to be a bad thing to say, but we're plugging in an x for our inverse function, which is like a y. It's going to pop out an x, which is going to go into this function, right? Because that's the whole thing. And f of x is just y. So whatever we originally plugged in will come right back out. This will be a little bit cleaner on the second one, because here we can go ahead and we can actually say, well, f of x is just a fancy pants way to write y, right? We said if you plug x into f, you get out y. So that whole thing is y. And then we can rewrite this f inverse of y. Oh, hey, that's the whole point of the inverse function. It pops out an x. So there we are. So this is why the composition should result in us seeing right back out whatever we put in as a variable. And typically that variable we put in is x. We also had a really good observation during class, right? Someone was like, you're cheating with sine because technically sine is not a one-to-one function. In order to have an inverse function, our function needs to be one-to-one. In class, we said that means it has to pass both the vertical line test and the horizontal line test. If it can pass both, then we've got something that is one-to-one. And unfortunately, a lot of our friends, our families of functions, don't pass this. If we wanted to make a list of things that are one-to-one versus not, things that will need domain restrictions in order to actually do some work on them, one-to-one, almost all of our linear functions are one-to-one. The exception, of course, being our horizontal and vertical lines. So as long as m, our slope, does not equal 0, or it is actually a number, we're good. So another one was any of our cubics, right? We did a cubic as one of the examples. Anytime we have a cube root, falls into the same family as one-to-one. Trying to think of other things that we had that were one-to-one. But we have a lot of failures. I mean, honestly, we have more failures in our families of functions as I'm trying to think about all of these functions we had. Our parabola fails. In fact, let me actually do these ones in red because failures are typically in red. Our parabola, our absolute value function from the last section, any and all of our trig graphs, right? Every trig graph, it feels like, fails us. The only ones that don't, by the way, are the inverse trig functions because they are defined in such a way that they're not problems. What else do we have? I was trying to think. Oh, our reciprocal function that we came up with. In fact, any even power function, same issue. Another one-to-one. Beyond our cubic and cube root, we also have our exponential. Bloop, bloop, and on the same vein, it's inverse the logarithm. So typically if it has an inverse, right, that inverse function is here. Oh, another one that is one-to-one but kind of funky is just our square root function. It works, it's half a parabola. You do have to kind of think about what happens when you go the other direction because you actually have to worry about the fact that you've defined a bigger function that has two sides when our original didn't. So this is why that graphing can be really useful when you might see a bit of a failure or something you could overlook in the composition of functions. So we got a lot of that. We found and evaluated them. So let's go ahead and just do a problem. So first problem I'm going to have us do, and then we'll revisit the one that I foibled in class just because it's worth talking about. I just turned my brain off when it came to doing all of the transformations and how they impacted all of those different values, but I think they're really worth going back and looking at. So for this question, we are said to find a domain where we are one-to-one and non-decreasing. Write the domain of the interval, blah, 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 blah. Okay, so let's just graph what we got going on here. We can see we've got an f of x. This is obviously a quadratic. It falls into our little family of parabolas. Its little parent function is the little sad parabola centered at 0, 0, opening up. And we only have one transformation happening to it. It is shifted to the left 7. So that's where my parabola is going to go. And welcome to Sketchland. I don't have to draw a good parabola. All right. So it has said we want this to be one-to-one. Right now we fail the horizontal line test. And we want it to be non-decreasing. And so this is just being picky. It doesn't really matter how we do a domain restriction. Typically we do it this way. When you look at how we restricted sine, we saw the exact same thing. Our graph of sine, we could have chopped it in other ways, but it is chopped usually from pi over 2, negative pi over 2 to positive pi over 2, so that we have this non-decreasing segment. So same thing here. We can chop this thing in half where the problems are at x is equal to negative 7, but we only want the non-decreasing side because that's just what the book has said. And so in that case, we need every x greater than negative 7. We can go ahead and include it, in fact, because it doesn't hurt us to. So we're going to say from negative 7 to infinity. That's the domain that we're going to have as our restriction. And if we wanted to check our work, you know where I'm going to go. Always, always, always. I'm going to go to Desmos. Oh, I forgot. Desmos. I'm going to graph this thing. And we were looking at y is equal to x minus 6 squared, right? Oops, was it minus or was plus 7? What is wrong with me? Where is our notes? Y plus 7. So I don't know why I did minus 6. Ooh, plus 7. All right. And then we want to check. We're just going to go ahead and add that domain restriction like we did in the logo question, the logo discussion board. We're going to say x is greater than or equal to negative 7. And we can see it's only that half of a parabola. We feel really good. We could also, if we don't want to do it like that, we feel like that's too aggressive, I want to be able to see my graph, we can just make a separate line with x is greater than or equal to negative 7, and it'll shade that side of the graph, sort of showing me, yeah, we're good here. We've got where those two things overlap. All right, so we've got our domain restriction. The last thing it asks us to then find the inverse. And so I think it was Dan, he walked us through this in class. Step 1, we're going to do exactly what the inverse does. Swap x and y. So technically this is y is equal to, we're going to say this is x is equal to y minus 7 squared. Step 2, solve. And this is where it doesn't really matter if you do this in a particular order, because no matter what, we're basically just trying to solve for the other variables. So this was my input. I want it to become my output. So I need to reverse this thing. So I'm going to square root both sides. I've got the square root of x. Typically, when we solve something using that square root, we have to do the square root principle, where we have to do a plus or a minus. We don't have to do that here. If I wanted to graph something that wasn't a function, then I would need the plus and the minus. But we only want the positive section because we've restricted this to the positive non-decreasing side of my parabola. And this is equal to y minus 7. And we can add that over. We get y is equal to square root of x plus 7 on the outside. So what was a horizontal shift to the left is now a vertical shift up. So everything is reversed. Was horizontal is now vertical. was down or was left, now is up. And then we can rewrite this last step as f of x, f inverse using that inverse notation. And then of course, if we want to finish this all up, make life happy and check our work, we can do y. I keep forgetting that I don't have my thing plugged in. Y is equal to, y is equal to the square root, and I always forget I don't need that either. Y is equal to the square root of x minus 7 on the outside. And you might also see that eventually that there's a lot of a pattern going on here. If it was happening on the inside, it's not happening on the outside. That's that vertical to horizontal swap. And then it has the exact opposite sign that it had before because we're doing that inverse function. So that's sort of a quick way to double check that everything makes sense with what you're thinking. I'm going to put back my restriction here. And then I will also graph my y is equal to x line so that I can see, sure enough, these things look like a perfect reflection of one another over that line. So I have a nice check. We can also check this mathematically. So let's do that as our last piece. I know you don't need any of this and no one's watching it, but just in case, we can go ahead. We know f of x. Let's just do f of f inverse of x. So I need to take f inverse, shove that all in here, right? So we're doing f of this big old square root of x plus 7. And f tells me that we're supposed to take whatever we have, add 7 to it. Oops. Did I really put plus? Oh, I wrote, my God, you guys are tired yelling at me over here. I even changed it when I was doing the actual problem because my brain knew that they had to be opposites. Whoop, whoop. There we go. Sorry, I copied down my problem wrong. So we need to plug in minus 7. Good thing we're doing like 20 different checks so I can find my mistake. So according to this, we add 7 to it, and then we square it. And the it in this case is the square root of x minus 7. The minus and the plus cancel, and we end up with the square root of x squared, which is just equal to x. When we have this sort of restriction going on, we don't have to worry about technically when you square root, something like that, you have the absolute value of x. You have this restriction that comes back on it. But this is our check. It worked. We're good.